Okay. So I want to thank the organizers for the invitation. I want to thank for the great program that's being put up on variational methods. So what I'm going to do is I'll just do a survey of all the recent progress in the existence problem for minimal surface. And then at the end, I'll talk about some new work I'm doing jointly with Fernando, and which is taking the field in a somewhat slightly different direction. Okay, so let me start with, I guess, the motivating question was really to Burkhoff in 1917, start with a paper of Burkhoff in 1917, and the paper is that every two-sphere with any metric always has a closed geodesic, And so after this paper, there were huge developments on the problem of existence of closed geodesics, and so I'll just select some few results that will be related with things I'll later talk about. And so there was an important result of Bowen from 73. Mistaken, let me see. Yes, from 72. And Bowen's result says that if we are on a closed manifold whose sectional curvature is negative, then almost all closed geodesics become equidistributed as the length tends to infinity. Become equidistributed as the length becomes large. So the phrase almost all is crucial because even on surface we can construct closed geodesic of arbitrarily large length whose accumulation set is neither a closed geodesic nor everything. So the behavior of a particular geodesic in negative curvature is very complicated, but with probability 1 it will not be, or they'll just become scattered all over. Actually, Bowen's result is not about the closed geodesic. So Bowen's result is about periodic orbits for Anosov flows, and the geodesic flow is a particular case of an Anosov flow. So, yes.
So almost all is
it's a measure you put on the unit tangent bundle, yeah. So almost all with respect to the Bowen-Margulis measure. So it then became crucial to understand the measure under which almost all was being considered. Okay. So then there's another result of Pugh Robinson, roughly 10 years later. This is from 83. And Pugh Robinson result is that for a C2 generic set of metrics, on a surface, on a closed surface, the set of closed geodesics is dense. The set of closed geodesics is dense. So again, the Pugh Robinson result, it's not about geodesics. This case is about Hamiltonian systems. They prove what was known as the C1 closing lemma for Hamiltonian systems. And the geodesic flow is a particular case of a Hamiltonian system, and so they get the denseness of periodic orbits. That's an interesting question here, which is a bit of a puzzling thing, which is it's not known of example of a surface for which, of a closed surface for which the set of closed geodesics is not dense. It's known examples of surface for which the set of closed geodesics is not dense on the unitangent bundle, but it's not known whether this projection on the surface becomes dense or not. So it's conceivable that for every surface, the set of closed geodesics is always dense on the surface. How do I phrase this? Open. So I think this is a question of Keith Burns. Are closed geodesics meaning our closed geodesic is the set of all closed geodesics. So
the union of the four.
That's right, yeah. Is the set of all closed geodesics always dense? Is the set of closed geodesics always dense? Always dense on sigma. Okay. And then there's the work on existence of geodesics continue, and there is an important result here. This is due to Franks, and it was a separate paper. Franks in '92, then Bangert in '93, and shortly after, Nancy Inkster, she gave a second proof in '93 as well. And the result is that every two-sphere has infinitely many closed geodesics. Okay. And this result is really about geodesics, even if Franks uses a bit of perspective Hamiltonian systems, and then Inkster, in her work, she replaces many of the arguments of Franks there. But this result is really about the existence of closed geodesics. It's not a result about orbits of Anosov flows or Hamiltonian systems. And so, motivated by these developments, I guess Yau, there's a conjecture of Yau from '82. Actually, if I'm not mistaken, the conjecture was made on a program on, I guess, geometric analysis that was done in '79 at the Institute and was only published in '82. But my impression is that the conjecture was also made at the Institute. Yau's conjecture in this case says that every closed three manifold admits infinitely many minimal surface. And so I think there are two versions to the conjecture. One where it just appears minimal surface without specifying whether it's embedded or immersed, and then later he explicitly asks for embedded ones. But in the original one, was literally that possibility. The possibility of being immersed was open. So around this time, there was the combined work of Pitts, but also this was '82, '81, and also of Shane Simon in '81. Their combined work shows that every manifold, every closed Riemannian manifold, admits one minimal embedded hypersurface. Minimal embedded hypersurface, which is smooth outside a set of codimension 7. Smooth outside a set of codimension 7. So then around this period, the research in minimal surface was extraordinarily active due to the work of Carl Sachs-Uhlenbeck, Shen Yau, and many more people. But it was mostly focusing on studying minimal surface of low index. And so there was essentially a period where there was not much activity regarding existence of minimal surface of arbitrarily large index. And so still in the category of low index minimal surface, this conjecture was solved in the hyperbolic case. So I'm going to talk about the solution because it's going to be relevant to what I'll say after, even if, to be fair, the minimal surface produced there, they will be immersed. So they'll not necessarily be embedded. So this is a consequence of two papers of Kahn-Markovich. So Kahn-Markovich. This was 09 and 010. And their setting is assume a three-manifold which is hyperbolic and closed. So a closed hyperbolic three-manifold. Then what they show is that there are essential and now I'll say what these words mean. There are essential, non-commensurable surface of arbitrarily large surfaces containing M3 of arbitrarily hygenous. No, not necessarily. Their result was not about minimal surface. I will explain how the connection is made. They never, when they state their result, they were not aware that they proved this particular case of the Yau conjecture. Okay, so it's a consequence of their result, but they don't say that. But it follows. I'll explain how. Arbitrarily hygenous. Okay, so let me explain these words: essential and non-commensurable. Okay. So essential, we say that a surface contained there is essential if its fundamental group injects in gamma, which is the fundamental group of the three-manifold. Okay. And the non-commensurability there, it's important because I want to avoid the following setting. Suppose we find the essential surface on a three-manifold, okay? Then if the surface is hygenous, what I can take is I can start taking coverings of that surface, composing that with the injection of the surface onto the three-manifold, and I get an infinite number of essential surfaces of arbitrarily hygenous. On the other hand, what I'm doing is somewhat formal. I'm just taking covers of a surface that exists there. And so non-commensurable is to avoid that. So two surfaces are commensurable if both covered by up to homotopy by a third essential surface. Okay. So because of this, now we know from the work of either Sack-Sullenbeck or Chen-Yau that in the conjugacy class of each essential surface, we can find the least error representative, which will be an immersed minimal surface. And of course, we have to exclude that for all these different conjugacy classes, we are not getting always the same guy, just taking different covers of it. And this is excluded by the non-commensurability hypothesis. And so using either Chen-Yau or Sack-Sullenbeck, we get that thus there are infinitely many minimal immersed surface. And these are all stable. Immersed surface. Okay. So I'll talk a bit more about the result. I'll say exactly what is the result from 1910, because this is going to appear at the end. So let's just say some more words about that. Okay. So So this is the sequence of two papers. In their first paper, they show just the existence of one of arbitrarily large genus, and then in the second paper they show that actually there are lots of them. So I'll get two definitions and then I'll state their second paper. So if sigma is essential, then its lift, it will be a disk in the universal cover, which is the hyperbolic plane, the hyperbolic space. Then lifts to a disk D contain on the hyperbolic space. So this is the picture. There's the hyperbolic space. I see it as a 3-ball. There's my fundamental domain. There's sigma there. And then it has a lift, which goes all the way to the three-dimensional ball. And of course, this has to be periodic. And so because things are getting squashed, it's getting more and more wiggly as we go to the boundary. And so the boundary of this disk is contained on the ideal boundary of the hyperbolic space, which is the same thing as the two-sphere. So this is contained on the two-disk. And we call this is a very important set. It's called the limit set. This is called the limit set, and just depends on the action of the way the fundamental group injects onto the surface, onto the gamma. Okay, so this is called the limit set. So this set can be extraordinarily complicated. For instance, there's an example of Cannon and Thurston where this limit set is really the whole sphere, right? So these things can become extremely complicated or extremely simple. For instance, if the surface is totally geodesic, then the limit set is just a circle on the two-sphere. And so, likewise, it's known that if the limit set has Hausdorff dimension 1, this is the result of Bowen, then the limit set has to be a circle. So if this limit set is a smooth curve, it has to be a geodesic circle. Okay. So the result of Kahn-Markovich, let me just put like this. This is the result in 10, is that, so let me see, let's make sure I get this right. So what they do is they fix epsilon positive, and then they show that for some genus large enough, arbitrarily large, for some G large enough, or for all large enough genus, they count the number of essential surface. But now they count the ones where the dimension, where the Hausdorff dimension of the limit set is less or equal than 1 plus epsilon. And of course, when you do this, you have to make an equivalence class. And the equivalence class is up to conjugacy class, which is like homotopy, and also up to commensurability. So they count this up to commensurability and conjugacy class. And they see that this number, it grows like g to the power of 2g. Okay, so in particular, it's non-empty when g is large, and then the result follows. So will be used this growth at the end. Okay. So there was this digression. Let's see. I'll just let's do like this. Okay, so that's it. So then let's see if I got the years right. Yeah. So let's call this theorem A. So this is due to Fernando and myself from some years ago. So in this case, we assume that the ambient manifold has positive Ricci. And then in this case, we show then there are infinitely many minimal embedded surface, embedded hypersurface. Which again are smooth outside the set of codimension 7. Okay. So in particular, Yau's conjecture holds each time that the metric is as positive Ricci. So this result is dramatically different from the Markovich because this minimal surface we produce, they will not be stable. So typically they're indexed. They become more and more unstable. So for us, this result was a bit of a landmark because the idea for the proof, I would say it's totally standard now. And the fact that with such a simple idea, we were able to already handle Yau's conjecture in such a large class of examples told us that we were doing something right. So then theorem B, this was we jointly with Kairi, Marcus, Fernando, and myself from last year. And in this case, we show that for a C infinity generic set of metrics on a given manifold. But now we make a dimension restriction. The dimension is between 3 and 7. The set of embedded minimal hypersurface is dense. Embedded minimal hypersurface is dense. Is dense. Okay. Then so in particular, Yau conjecture holds for a generic set of metrics. And then shortly after is what I'm going to call theorem C. This was due with, again, Fernando, myself, and Antoine Song. We show that not only they become dense for a generic set, as we can find a sequence of minimal hypersurface that actually becomes equidistributed on the manifold. So for a C infinity generic set of metrics, on a manifold, again with the same dimension restriction, then there is a sequence sigma I of embedded minimal surface, minimal hypersurface, such that they become equidistributed, and the equidistribution we obtain is the following: that if we pick an ambient function, continuous function, such that for every continuous function, if we average the first n, if we average the function f over the first n minimal surface, and we divide by the total volume, then when we make n go to infinity, we recover the average of the function over the whole manifold. Okay. So again, so theorem B, it's the analog of the Pugh-Robinson result. Theorem C is the analog of the Bowen's result. But of course, the starking difference is that there's no Hamiltonian system or axiom A flows underlying this. So the equidistribution in denseness comes from a different phenomena. Okay, and this somehow sparked a burst of creativity in the area, and then within 6 more months, the Yau conjecture was solved, and also this multiplicity one conjecture for 3 manifolds. So I'll just state the results. So then shortly after, there's a result of Chodos and Mantoulidis. In 18, which says that, so I will state their result in a form which is somewhat convenient to the things I'm talking about, and then I'll say some words about it. So is that for a bumpy metric G, for a bumpy metric, on a 3 manifold, on a closed 3 manifold, there is sigma k, a minimal embedded hypersurface, minimal embedded surface, with Morse index k, and the area like cube root of k. Okay, this for all k integer. So actually, if I state this result, so this, to be fair, this result is a consequence of the Chodos-Mantoulidis plus work of Gaspar and Guaraco. What Chodos and Mantoulidis show is this: they prove the multiplicity one conjecture that Fernando and I had conjecture for the Almgren Pitts min-max. They prove that conjecture for the Allen-Kahn equation, and then having that conjecture, this follows from this program that Fernando and I developed when we were trying to prove Yau's conjecture. Okay. And so and then I guess some months later, Antoine Song in 18, he closed the problem, and he showed that every closed manifold, again with the same restrictions, admits infinitely many minimal embedded hypersurface. Okay. So what I'm going to do now is so the common feature among all these 5 results is that they use, in a fundamental way, this notion of volume spectrum. So what I'm going to do now is I'll just recall a bit this volume spectrum, explain just very loosely how the volume spectrum can be used to handle theorem A, B, and C, and then I'll talk about some slight new direction that I'm doing with Fernando and now. Okay. So let's do a brief definition here of the volume spectrum, because that turns out to be an essential concept in all these 5 results. Okay. Okay. So the setting here is I have the space of This is mod 2 codimension 1 cycles. Mod 2 codimension 1 cycles. It's like the space of all embedded hypersurface. And there we have the mass. T goes to the mass of T, which is like the volume of T. Okay, and the volume spectrum can be defined in the following way. So the P width of M on the manifold M with respect to a metric G. So we can define this, loosely speaking, as the nth among all lambdas, such that we can put p-dimensional projective space inside the inverse image, inside the set of all hypersurface whose area is not bigger than lambda. Okay. So if lambda is too small, this set is contractible, and so of course you cannot embed a p-dimensional projective space there. But if lambda is too big, this set has it's weakly homotopic to RP infinity, and so it should have lots of p-dimensional projective space, and there's the critical one such that below that one there's none, and we take that value. So this is not the correct definition, but it's a good way to think about the things. It's the shortest way to write the definition without lying too much. Yeah.
Does it have to be essential in some sense?
What does that mean?
Well, in the same sense that it injects on homotopy.
Yeah. So I mean, that's right, of course. The way to state this is that there's an element in singular cohomology, and you need to the pth power of that element in singular cohomology cannot vanish on the set. Yeah. So this is the way you rephrase it. But what it means is this. Yeah. And so this sequence is called the volume spectrum. This is the volume spectrum. Okay. And so there's this volume spectrum was considered in a very general setting by Gromov in the 80s, and then Guth restudied again some years ago. So I'll just say the result. So this is Gromov in 87 and Guth in 09. And what they show is that the volume spectrum grows like the n+1 root of P. Okay. And then some years later, jointly with Lokomovich, Fernando, and myself, we show that this volume spectrum obeys Weil law. So volume spectrum obeys a Weil law. I'll just say what volume spectrum obeys a Weil law. So what this means is that there exists some universal constant just depending on the dimension, such that the limit when p goes to infinity of the pth element divided by their growth power, this is a universal constant times the volume of the manifold with the appropriate scale invariant power. So that this volume spectrum should obey a Weil law that was conjectured by Gromov around in a paper I think in 2005. Okay, and so this Weil law for the volume spectrum turns out to be the key ingredient to do B and C. Okay, so okay, good. I still have the theorems on the board. That's good. So I can just do each here so that we see them. Yeah. Okay, so let's erase it and write just. So we will remember this. Okay. So I'll just say how the. Oh, okay. Sorry. Yeah, there's another key ingredient, and I was forgetting, because on the face of it, there seems to be no relation with the volume spectrum and minimal surface. The relation is provided by the min-max theorem. So let me write that theorem, because that's also a crucial ingredient. So the min-max theorem, this is due to Pitts, Shane-Simon, and in the version I'm going to state, Fernando and I also add a contribution here. And the theorem says that for every integer p, there exists a minimal sigma p minimal hypersurface, embedded hypersurface, with again a single set of codimension 7, but let's not write that. There is a minimal embedded hypersurface with possible multiplicities. Such that the p width is just the area of this minimal embedded hypersurface. Okay. So in the same way that the Laplacian spectrum is realized by eigenfunctions, what this theorem says is that the volume spectrum is realized by minimal embedded hypersurface. So my contribution of Fernando and I was to extend the theory from homotopes like Pitts and Shane-Simon do to allow for cohomologies. So essentially, our contribution was to prove some a priori bounds for the Morse index of this minimal surface, and that allows to take sequences and limits. So these are the two ingredients: is the Weyl law and the min-max theorem. Okay. So now let's just see how these things come together. For instance, for theorem A. So basic idea behind the proofs. Behind theorem A, B, and theorem C. Okay. So let's do for theorem A. So for theorem A, which is if you have positive Ricci, you have infinitely many. So the argument there is assume only finitely many minimal surface, minimal hypersurface. Okay. Then we use positive Ricci. We show that positive Ricci implies that the p width grows at least linearly. That the p width grows at least linearly in p. And of course, this is a contradiction with either the Weyl law or the Gromov-Good theorem, because we know that it grows sublinearly. Okay, and so this contradicts the Weyl law, or growth contradicts the growth. Okay. And so there has to be finitely many. For theorem B, the argument is also by contradiction. And now the idea is to contradict the continuity of the volume spectrum in terms of the metric using the Weyl law. So let's do for theorem B. So let's do I'll just consider a simple toy case, which is the toy case is just an open set on the manifold U, on the manifold M. This is M, and we take here an open set U. So U open containing M. Okay. And now suppose we have what we show is that suppose you have a one-parameter family of metrics, which is just a supported inside U, essentially. Suppose there is GT is a one-parameter family of matrix. Family of matrix supported inside U. Okay, so the metrics are all the same outside the set, and here they could just do, wiggle the set or do whatever it feels like. And they have the property that no minimal hypersurface ever intersects U, such that no minimal hypersurface ever intersects U. Okay. If this is so, then essentially we show that this function that sends t to the p with respect to the metric gt has to be constant for sufficiently large p is constant. We need some more conditions, but essentially this is what we show is constant. Okay. But of course, this contradicts the Weyl law, because if I do a deformation that increases the volume, then I know that eventually this cannot be constant, because the Weyl law says that as p gets very large, the p width is this fixed term times the volume of the manifold, right? And so it cannot possibly be constant for every one-parameter family. And so this contradicts the Weyl law. Contradicts the Weyl law. Okay. So for the third theorem, the argument is a bit more involved, so I'll have to oversimplify it. So the argument is considerably more subtle. And so let's suppose that now we don't have one set U, but we have like k sets. U1, U2, say U3, U4. So suppose we have U1 to UK, disjoint open sets. Open sets, okay? So in this case, given these disjoint open sets, what we show is the following. We find a k-parameter family of matrix, GT, but now it's on a k-dimensional cube. Okay. We find a k-parameter family of metric, which is just a tiny perturbation of a given metric, such that it has the following property. So we take this k-parameter family of matrix, and then we consider this function that depends on t. So that we look at the function. Let's just call this WP of t, which is this function just comes from taking the log on this identity and pulling that side, or literally just taking the log of this identity and putting the volume term on that side. So the function will be the log of the p width of m of g of t minus then going to be the log of the volume of m of g of t times n over n plus 1 minus the log of p over n plus 1 minus the log of alpha n. Okay. So we have the family of matrix. We can always consider this function. And the observation is that this family of matrix is made in a way. So essentially the family of matrix just amounts to each parameter k just changing the metric on separately on each of these k sets. And this is cooked up in a way that such that if t bar is critical point for this function wp of t bar, then there exists a minimal surface, minimal hypersurface, embedded hypersurface in M for the metric GT bar that is equidistributed with respect to that set. Equidistributed with respect to U1 and to UK. And of course, from the Weyl law, we know that as p goes to infinity, we know that this goes to 0. And so if you have a function which is going to a constant, eventually it should have some critical points. Of course, then the proof ends up being more involved because the function, it's not differentiable everywhere, right? But this is the very general speaking, just the brief idea. Okay. So let's see. Yeah, I have shortly less. I have like 10 minutes left, so let me. I'll just start there. So I'll tell you about some new things I'm looking now with Fernando. Okay. Okay. So the things I'll talk about. This is joined with Danny Calgary and Fernando Marquez, of course, and myself. Okay. So the setting we are looking at is a three-manifold, closed three-manifold, which is hyperbolic, admits hyperbolic metric, and then we look at this set S of epsilon, which is the set that Kahn-Markovich showed that it's adds lots of elements. This is the set of essential surface sigma contained on M3, which have the property that with the Hausdorff dimension of the limit set less or equal than 1 plus epsilon. And we have to make an equivalence class, and the equivalence class is conjugacy and commensurability, up to conjugacy and commensurability. Meaning we identify two homotopic things to be the same, and also covers of a guy that's already there I also identify to be the same. Right? And so, for instance, so let's put this remark, is that if I put epsilon equals 0, then this is empty for many cases. Okay. Because if I put 0, then this would be essential surfaces limit set as Hausdorff dimension 1, and those are known to be circles, and so which means that the three-manifold would have to admit a total geodesic surface, and it's known many cases where there's simply none. Okay. And so now we put another metric on the manifold, which is not necessarily the hyperbolic one. This is just some metric. There. And given a metric, so if we give a representative inside this set of homotopy classes, we can take the least error representative with respect to this metric, right? We define this to be the inf, to be the, let me write there. This is the inf of the area, is the least area surface inside the homotopy class given by this set of conjugacy classes and up to commensurability, such that sigma is in pi. Okay, and this is area with respect to the metric G. And then we are interested in counting the things as the area gets very large and epsilon very, very small. So now we consider this number. We call it E of G. And let's see, hopefully it will fit here. And so this is the, so I'm going to count so this, of course, is achieved by a minimal surface. So I count all these minimal surfaces whose area is less or equal than a number L, where pi is a homotopy class there. And now, because I know there are lots, I take its log, and then I divide by L, natural log of L, and I make the limit when L goes to infinity, and then we also make the limit when epsilon goes to infinity to make sure they try to be as virtually total geodesic as they could possibly be. And so the theorem is that, so assume that the sectional curvature of G is less or equal than -1, then this number is greater or equal than you get for the hyperbolic metric, which is 1 over 2 pi. This is the hyperbolic metric. And equality implies that G is hyperbolic. Okay. Okay. So so I'll just say some words about the proof, and then I'll finish.
Sorry, but can't we assume what?
Assume the sectional curvature of G. Assume the sectional curvature of G is less or equal than -1. Okay, that you are more curved than the hyperbolic metric. Then this number goes up, and equality gives you 1 over 2 pi. Okay. So to get the inequality, so let's not do the inequality. I'll just say some words about it. So to get this and to compute this, essentially, I mean, it just follows from using Gauss equation, the Kahn-Markovich theorem about the growth of that set, plus some important work of Karen Uhlenbeck on what's called almost Fuchsian surface. So this follows, I'll just write here, just follows from Gauss equation plus Kahn-Markovich plus Uhlenbeck. Okay. So let's look at the rigidity case. Suppose that this number equals what you get for the hyperbolic number. How can we get the rigidity, right? Why does this imply that G has to be hyperbolic? And the interest in the proof is that to prove this, we have to use a theorem in dynamical systems. Okay. And this is the thing I want to show you. Okay. So if we chase the equality there, okay, then what we get is if we chase the equalities, we get that infinitesimally G equals to the hyperbolic metric, and then we have to use the theorem dynamical systems to go from the infinitesimal to the global thing. So let me tell you what we get. We get that, so in this case, if equality, then we get that existence of a totally geodesic disk, D, but now total geodesic with respect to the metric G, not the hyperbolic metric, such that the D is the limit of coverings, is the limit of lifts of non-commensurable surface, minimal surface, sigma I when I is in N. You get it? The second property is that the boundary of this disk is just a geodesic circle in the boundary of the ideal boundary, which is the tree-sphere. And the third property is that this disk has sectional curvature. The sectional curvature of the tangent plane of the disk equals -1 for all x in the disk. So the picture is the following. There's the 3-ball. There's our fundamental domain. And then we get this disk, which is going to be wiggled because it's just total geodesic with respect to this metric G. So this is the disk. This is the disk D. And I know that this disk is total geodesic, and that the sectional curvature of this disk is always -1, right? I want to get that the sectional curvature of the metric at every point is also -1, not only on the disk. And so the way we do this is, for the same boundary condition, there's a total geodesic disk for the hyperbolic metric. We denote this, right? This would be the first step, is that choose a total geodesic disk for the hyperbolic metric, which has the same boundary, such that the boundary of this disk is the same boundary as the other disk, D. Okay? So which would be that guy there. And now the theorem we used, it was proven by Ratner independently and by Shah. And the theorem says that there are only two possibilities for the total geodesic disk. Either possibility A is if I project the total geodesic disk on the fundamental domain, I get a closed surface. Or B, which is if the disk does not project to a closed surface, then it's because it's dense in the Grassmannian. D is dense in the Grassmannian. In Grassmannian. Or the way usually people phrase it is on the frame bundle, is Grassmannian of M. So the picture here is this total geodesic disk either projects to a nice surface, or if not, then when I project there, it just becomes dense and all over. So this theorem is somewhat, I don't know how surprising this is, but let me tell you one thing. For geodesics, this is not true. So if you have a geodesic on a surface, then if you take a geodesic on the hyperbolic disk and project to a surface, it will not either be dense or a closed geodesic. So its behavior can be very, very chaotic. On the other hand, for total geodesic disks, that's not the case. Either they project to a closed surface or they are dense. And so the essential, okay, so I'll just finish now. So what we show is that we rule out this case because we show that if the projection is a closed surface S, then we show that these limiting guys, these sigma i's, they will be homotopic to a covering of S, and that will be ruled out because I'm assuming they are non-commensurables. And so because of this, it's the second possibility that holds, that this total geodesic disk projects to everything. And because D is also total geodesic, then we can see that in this case, D also projects to everything. And so if the sectional curvature of the tangent plane of D is always -1, if this projection on the Grassmannian is dense, then the sectional curvature of the metric G has to be -1 everywhere. So essentially, A we rule out, and B we show that implies that D is dense in the Grassmannian, and so which implies that G has to be hyperbolic. Okay, so I'll just stop here. Sorry for taking a bit longer. Thanks.